Hello everyone, so this is the second set of video lectures for percent concentration. So in the previous video we talked about percent volume and percent mass volume. So in this lecture video we're going to be talking about molarity and a very close relative molarity called osmolarity. So we're going to talk about molarity first. So molarity, and again, for any unit concentrations, and you should be aware of this now, is always going to be how much solute is going to be expressed on the numerator, and the total volume of solution is always going to be expressed in the denominator. So in this case, molarity is just the moles of solute over 1 liter of solution. For now, ignore the 1,000 mils. That is going to be for conversion, like in the purposes in later problems. Okay. Now, notice here that the solute is not expressed as milliliters or as grams, but as moles. But also know that the moles of solute can be calculated by finding the molar mass of a particular substance. And again, that is actually in your exam reference sheet in the box which we use for stoichiometry. Okay? So we might as well just do an example. So what is the molarity when 50 grams of sodium chloride is dissolved in 500 mils of solution? So we have a couple problems here. Again, note that molarity is moles of solute over 1 liter of solution. We need to convert this mils into liters. We also need to convert this into moles. This we have done in stoichiometry. This we have done in metric system conversions. Okay, I hope that you remember those, otherwise you're going to be in deep trouble with this module. So the first thing is we're going to convert the grams of sodium chloride into moles of sodium chloride, and that's you take the given grams and you multiply it by 1 mole sodium chloride over 58.44 grams of sodium chloride. Where did this 58.44 grams of sodium chloride came from? This came from the periodic table. And recall also that in your exam reference sheet, the first step that you go from mass to moles is says right underneath by the arrow in a ratio, it will say 1 mole given. Okay, I'm sorry about this, over molar mass given, right? Anytime you see the 2 capital letters MM, molar mass, guess where you go? You go to the table, periodic table. All right, so this is how we found the 58.44. You took the atomic weight of 1 sodium and you add that to the atomic weight of 1 chlorine, and that's how you came up with 58.44 grams. Again, this is also a dimensional analysis problem. You do the math, it came out to be 0.856 moles. We're still following the rules for significant figures, 3 significant figures, 3 significant figures. So this is taken care of. We now have this. However, we have this other problem. There's 1,000 mils in 1 liter. The mils cancel. We're just left with 0.5000. Okay, we need to have 4 significant figures. Now we have moles. Now we have liters. What do we do next? We do a division. Moles of sodium chloride on top over liters of solution on the bottom. That's how I came up with this answer. 3 significant figures here. 4 significant figures there. Our answer has to be 3 significant figures. So in this case, just note that the moles of solute can also be taken from grams of the solute, as long as you know how to go from grams to moles, which is again in your stoichiometry box of your exam reference sheet. Are there variations for this problem? Of course. All right, here we go. Another similar example. What is the molarity when 120 grams of sodium chloride is dissolved in 2.5 liters of solution? So in this case, we do not need to do this conversion that we have done previously because the solution is now already given in liters. Okay, so the only thing we need to do is we need to convert this into moles of sodium chloride, which is going to be similar. I should erase a lot of this, right? Which is going to be similar to what we've done here, right? The only thing that we're going to be changing is we're going to be changing this 50 into 120 grams. Same thing again, so 120 grams, 1 mole sodium chloride over the molar mass of sodium chloride. That gives you 2.050 moles sodium chloride. We take that number and then we divide that by the volume of solution in liters. Okay. Which gives us 0.82 molar sodium chloride. So when you see the big M, it's molar or molarity sodium chloride. Okay. I hope that makes sense. Other variations for this kind of concentration? Sure. Okay. So here's a variation. So in this case, we're starting with a molarity, and we're starting with mils, and we're asking how many grams of sodium chloride is in a 200 mils of a 0.10 molar solution. Now, anytime you see molar, you always need to understand that the big M is actually moles over 1 liter. So this is going to be actually expressed as 0.10 moles of sodium chloride, I'm sorry for the handwriting, over 1 liter. That's the same as 0.10 m. Same. So in order for us to eliminate the liters and just and get moles, we need to first take this 200 mils. And again, this is where this 1000 mils come from, because if you express this instead of 1 liter and express it as 1000 milliliters, what happens? This mils will cancel that milliliters. And so the first answer is 0.020 moles sodium chloride. But again, the question is how many grams? Right? So we've done this again before. How many grams? So you go from moles to grams. All you're doing is you're expressing the molar mass in the flip ratio. So instead of the grams on the bottom, it's now going to be the grams on top, because again, you're trying to get rid of the moles. And so in 0.020 moles, there's actually 1.2 grams of sodium chloride, which means that the way someone made the solution, sorry, okay, so I should erase a lot of these things. So the way that someone made this solution, right, is in 200 mils, you could possibly get a 0. And in this case, a 0.1 molar. You take 200 mils and you just dissolve in it 1.2 grams of sodium chloride. In fact, FYI, I misspoke. It's not 200 mils. You actually add 1.2 grams, fill it to the mark at 200 mils. So if you have a container, you put salt in the bottom, 1.2 grams, and then you put water until the meniscus actually reads 200 mils. Okay? So that's actually how you would do that problem. So kissing cousin, or actually the sibling of molarity, is osmolarity, and you can tell that this is actually related. Why? Because the word molarity is still in there. The only difference is there's an os, just like the Wizard of Oz, molarity. Okay, whatever. So osmolarity is actually quite straightforward. This is just molarity times the absolute value of the negative charges plus the positive charges. What does that mean? So I might as well do an example here. So what is the osmolarity of a 2.5 molar sodium chloride solution? So again, the molarity is given to you already. So this molarity is already here. What we need to figure out is what is the actual sum of the charges. If we write a dissociation equation for sodium chloride in water, sodium chloride dissociates into the sodium ion and the chloride ion. So we have a +1 and a -1 charge. However, you can see that this lines means the absolute value, which means that what happens is you actually add 1 plus 1, because -1 is just 1. If you take the absolute value of that, and that's where you get this number 2, because you have a +1 charge and a -1 charge. You completely disregard the negative. That equals 2. This is actually how you came up with this portion here. And so that's actually how that number came to be. So 2.5 times 2. So the osmolarity of a 2.5 molar solution is it's actually 5 osmolarity for sodium chloride. If this was, let's say, I don't know, sodium nitride in this case. Sorry, folks. The overall charges would be a +1, right? And a minus, actually I messed this up, folks. Why did I put the 3 there? The 3 is supposed to be on the other side. And a -3. So the charge in this case is +1. And take the absolute value. The absolute value of -3 is +3. You add +3 and +1. The total charge for this ion would be 4, right? So you would multiply 4 times whatever molarity that would be. Okay, so that's molarity. So again, molarity is based upon the charges, and the charges are, you don't consider negative charges, you just take the absolute values of both charges. Okay, so here's a much more complicated example. What is the osmolarity 120 grams of magnesium chloride? This is solving that. So again, remember, we need to get to molarity first. So we need to convert all of these things into molarity first. Now again, remember, molarity is moles over liter. So we need to convert this into liters, and we need to convert that grams into moles. All right, so first things first, convert 20 grams into moles, get that number, check. Convert this mils into liters, check. Do the division because it's moles over liter. This is the molarity, 0.323 molar magnesium chloride. That's fantastic. And now, so we have this now, check. Now we need to multiply this by the number of charges in magnesium chloride. There's actually a straightforward way that you can do this. And the key is you say, oh, magnesium has a +2 and chlorine has a -1. What's the overall charge? If you take the absolute value of this, it's 3. Right? +2 -1, 2 + 1 equals 3. So we just take this molarity times the number of particles, which is 3. The charges actually in the particles. And that's actually how you came up with 0.92090 osmolarity magnesium chloride. The other way that you can actually, if you're confused about charges, is you actually use a balance equation. So here we actually have 1 magnesium and 2 chlorines. Here we actually have 1 magnesium and 1 chlorine. What number do we need to put? We actually put a 2 in front of the chlorine. 1 plus 2, that is also another way that you can actually calculate the number of particles that you multiply the molarity with. Okay, I hope that makes sense. If in the previous example, which was the sodium nitride, we know for a fact if this dissociates, we actually have 1 sodium plus 3 nitrogens. And so we actually add the 1 here plus the 3 here. We actually get a 4. Right? But again, the other thing that you need to understand is you need to make sure that you understand that something is soluble in water. If it's not soluble in water, whether it's a solid or liquid, all of this you don't need to do any calculations. Because why? Because that solid or that liquid is not gonna, in this case, break apart in water or not gonna distribute itself evenly in water anyways. Okay? So very, very important.